however much you want, we can find a property right that says something like, oh, you have the right to pollute so many hundred tons of this pollutant, and then we can allow some kind of trade in those claims, and that's a way to implement effectively a Coasian solution to the pollution problem. Okay, so there's two parts here. Notice that this is not now any longer a purely private arrangement, because government plays a very critical role here in the assignment of property rights under this scheme. And once they've assigned the property rights, they can step back and let bargaining or markets do the rest of the job for them. But initially, the assignment of property rights is something that the government has to be involved in. Okay, so let me go over the general idea of cap and trade in a little bit more detail. So here's one way to do it, one way of thinking about assigning property rights. So the government takes a guess at what the appropriate level of the pollution is. Okay, so they can do some blackboard exercise like we've done perhaps, and they take a stab at what the optimal level of pollution may be. And it doesn't have to be a very good guess. The important thing here is to assign property rights, not to assign the optimal level of inputs. So you can call this guess S. So the government then creates a right for the firm to pollute as much as S. Okay, so they're not allowed to pollute more than they're not allowed to pollute more than S. Possession of one of these contracts allows you to pollute 1 ton of some noxious substance, for example. And so the government assigns these rights to produce this quantity of air pollution to the polluting firms. So notice something that's important here, which is if we're going to give the rights to the firm initially is not harmed by the imposition of this scheme. If they are currently using something like about S hat, and the government says, okay, you can use S hat, they're not harmed by that in the least. There's no reason for them to oppose the imposition of this cap and trade scheme politically. Okay, so the government assigned these rights. I just suggested that they could be given to the polluting firms. That might be a way to make the cap and trade scheme politically palatable to everyone in society. But in principle, they don't need to be. If the government has the political will and ability to take the de facto polluting right away from the firm and give it instead to the people who are downwind, that would be a perfectly reasonable assignment of property rights as well. We'd also expect that to lead to an efficient allocation of pollution. But you'd be taking away something from somebody who had something that might be a politically difficult thing to do. Okay, so if we give the pollution rights to the firms, then what we're doing before the scheme is feasible. The firm has the right to pollute S hat if it wishes to, but it doesn't need to do that any longer. What it could do instead is decide to produce a quantity of pollution related to S hat, which is smaller than S hat, and take the extra permits it has and sell them to anyone who wanted to buy them. Now, who would want to buy them? Well, the people who are downwind might want to buy them. So the individuals here near the factory who would like to see less pollution should be willing now to pay the firm in order to have them reduce the amount of pollution that they're emitting. And since we have a property right now and tons of pollutant, that's a perfectly feasible sort of exchange. The people who live downwind can just buy from the firm the right to pollute and take that. They can take that right to pollute and either sell it to some other firm someplace else, so they won't be polluting their backyard, or they can just tear it up and there will be that much less pollution. Okay, let's see. Okay, so it's interesting. I actually think there's an opportunity. If you look at it, there are very well-established cap and trade markets, mostly in Europe. There are also regional markets in the U.S. Most of the exchange in these markets occurs not between individuals and firms, which is the story I just told. Instead, they're traded between different firms. So if a firm in one location has the right to produce S hat, and a firm in another location has the right to pollute some other amount, but the marginal benefit of production in this other location means that they'd like to ramp up production, they can offer to buy the right from this other firm. And it's the exchanges between firms like that that really dominates the market we have in the cap and trade markets we have. Now, I think it's interesting. There is a sort of there's some individual markets for global greenhouse gases in particular that individuals sort of participate in the U.S. in particular. Those are set up differently as a rule. So there are plenty of firms you can Google for this easily enough who do something like say, well, what we're going to do is set up a tree plantation, and you can pay us to plant a tree, and that'll absorb so many pounds of CO2, and if you pay it to do us, we'll absorb the CO2, and that'll be great. So there's a fairly active individual involved in those kinds of markets. But the marginal cost of removing a unit of CO2 from the atmosphere via these little voluntary schemes where you're paying a firm to undertake some new investment to reduce global greenhouse gases, the marginal cost right now, you can Google it. I checked it a couple days ago. I think it's about $14 a ton. So if you want to, as an individual, you can go invest in a firm who's going to plant some trees for you, and $14 will reduce the carbon in the atmosphere by a ton. But the price in these organized markets that are mostly used by firms, the marginal cost of a ton of CO2 is much lower than that. So if you were a consumer and you wanted to get rid of 2 tons of CO2 for $14, it would be much better if you could participate in the more organized firms that are dominated right now, more organized markets that are dominated now by inter-firm exchange. I think it's an opportunity for someone to set up a firm that acts as a broker aimed not at firms. So these brokers exist already. There are very important brokerage firms that cater to corporations that want to pollute and arrange to buy and trade the necessary permits on these exchanges. But there's not really an easy way for an individual to buy those pollution permits or carbon offsets or whatever on these organized exchanges. I think it's an opportunity for an entrepreneur to do that, to have a retail brokerage that undertook that. Anyway, that's effectively as an aside. Okay, we can also though assign the pollution rights to the individuals to finish this up. Remember, the assignment of property rights, the fact of the assignment is critical for Coastal work, but how the property rights are assigned is unimportant. So you can take all the pollution rights and give them to the individuals. This is kind of like the idea of having the individuals buy the firm. So you just give everyone downwind a bunch of right to pollute, and so now the firm is not allowed to produce any steel at all unless they purchase those rights. And so they can now approach the people who have those permits and say, hey, we really want to produce some steel. We'll pay you handsomely for the right to pollute a little bit, and presumably something can be worked out. Yes, Hillary? Yeah. That's very good. So when I say it's not, so allocations will be efficient regardless of the assignment of property rights. So the fact that they're efficient doesn't say anything about the distribution of profits or consumer surplus after the fact. So efficiency is not affected by how property rights are assigned, although it depends critically on having them be assigned. That's good. Okay, let me keep going. So I want to change to another example. So this is a traffic congestion example. We've talked a little bit about this as well. So I'm going to work through this a little bit carefully. So mathematically, the nature of this problem is going to be a little bit different than the kind of problems we've solved so far, because what I'm going to think about is a discrete problem facing each of a bunch of different workers about whether to drive to work or whether to take a bus. Okay, so that's the idea. It's a choice between driving and taking mass transit. The externality I'm going to worry about here, there's some pollution externalities too, no doubt, but the one I'm going to be concerned with here is the congestion externality. And so there's a couple of really good local models we have. I sent out on BSpace a couple of articles that touch on this, so I hope you get a chance to look at them. Just they're easy, fun reading. One nice example we have is the congestion that occurs when people cross the Bay Bridge. And so just in recent years, there have been attempts, pretty successful by some measures, to vary the level of the toll going over the bridge in order to induce an efficient mix of people driving between the East Bay and San Francisco and taking the BART. So that's they've accomplished that by raising rush hour tolls effectively. Okay, so that's one model. Another model, which I'll come back to it in a little bit, is a proposal to limit driving within San Francisco during certain hours. And so the idea there is if you go within some region of San Francisco where traffic congestion is currently bad, you automatically pay a toll just to go there. So it's not a bridge toll, it's a going into northeast San Francisco toll with your automobile. So schemes like that have been implemented most famously in London, but also some other cities. And there's a serious proposal to do something similar in San Francisco, which hasn't been acted on yet, but it's something that we might see in the next decade or so. Okay, so here's the setup. Enough talk, it's time to do some math. So I want to think about the problem facing a given worker. Okay? And in my story right now, everyone's going to earn a wage W. So I'm going to try to change this a little bit later on, but right now everyone earns the same wage. Okay, so you can think of that as being related to the wealth of the worker or just the marginal product of their time, perhaps. But that's the setup. So everyone earns a wage W, and just to keep things simple, I'm going to assume that the only cost of commuting is the time cost. So you can either take a bus or you can drive. All you care about is the time spent. So I'm going to ignore the cost of gassing up your car and maintaining it, or the cost of the BART fare, just not because it's realistic, but just because I want to keep it simple. So the only cost here to commuting is how long it's going to take you. Okay, so the worker has a choice. They can drive a car or they can take public transportation. I'm going to assume, this is another way to keep things simple, that if you take a BART, it takes 1 hour, period. So we know right at the beginning that the cost to taking public transportation to the city, we'll use this word. So the cost of, cost of bus is equal to W. That takes 1 hour to commute. Your rate is W. The other thing you can do is to drive a car. The catch, if you drive, is that the cost of driving is some quantity phi. That says P. I really need to say rho squared, and times W. So this is, W is still the cost per unit of time you spend. Phi times rho is going to be the total time you spend. So this is time spent, and this times W is the cost of that time to the worker. Rho here is going to be, I'm going to define that as the proportion of people who drive, or the proportion of workers who drive. So it's a number between 0 and 1 inclusive. And you can see if everyone drives, then rho is equal to 1, so the total cost is PW. The idea is that the more people drive, the longer it takes. So conversely, if nobody's driving, then the cost is 0. You get there just actually instantly, which is kind of nice. Yeah. All right, so there's a cost which is of driving, which is increasing in the number of other people who are doing it. And so that's the externality. There's a congestion externality that depends on this phi in this row. So this is this is the cost of driving. Okay, is that setup clear? Yes. Phi is think of phi as being the cost of congestion. So it's if half the people, it's it's the cost. So if it's a big number, it's more costly to drive in terms of time. If phi is lower, the cost is also lower. So think of the congestion parameter. Okay, other questions? Okay. All right. So the first we're going to follow a sort of familiar pattern here. So we've got a bunch of workers. They're all making the same decision. The decision is whether to drive or to take the bus. And so put yourself in the position of one of these workers. And this is important. We're going to assume that each worker is small enough in the entire population that they don't regard themselves as having any effect on rho. So if I decide to drive across the bridge instead of taking the bus, my own individual impact on congestion is negligible. So we're going to ignore my impact on rho. Okay. All right. So you face this problem: taking the bus or driving. What determines what you're going to do? How will you decide? Yeah, so you'll do whatever the lower cost option is. So there's just a couple of possibilities. These costs, we're assuming everyone's the same right now. So these costs are the same for everyone. So it's just a couple. There's 3 possibilities really. So let's say initially that let's suppose that the cost of driving is smaller than the cost of taking the bus. Then what will happen? Yes. W is the wage, and we're assuming that the bus is free. So the only cost is time cost here. Yeah. Okay. So if it's cheaper to drive, what will you do? What will everyone do? If everyone drives, and if phi is large enough at least, is it possible that this can be less than W? Okay, no, so is that your argument clear? If phi is large enough, and if everyone drives, this is 1, then as long as phi is greater than 1, this can't attain an equilibrium. So this is not possible if phi is bigger than 1. Everyone's wage is the same. I'm going to come back later to a case where a lot of you are different. Yeah. Okay, let's put it out this way. Is it possible that everyone will decide to take the bus? Well, so if everyone takes the bus, then what's rho? That's 0, so this cost is 0. So provided W is positive, this is not possible, provided W is positive. All right, so neither of these things can obtain an equilibrium. If this is true, then everyone will switch to driving. If this is true, everyone will switch to taking the bus. But with these 2 restrictions, neither of those things can actually be true if everyone's doing those things. And so as a consequence, there's only one possibility, which is that in equilibrium, it has to be the case that W is exactly equal to phi times rho squared W. Is that argument clear? Okay. All right, so that's the sort of equilibrium condition we're going to make use of here to characterize the private outcome. Once we've got this thing, we can just solve for rho. We can figure out what proportion of people are actually going to drive. So this implies, W cancels. So this implies immediately that phi is equal to the square root of 1. I'm sorry, rho is equal to the square root of 1 over phi. Okay, so this is the proportion of people who will choose to derive the equilibrium. Now, there's an interesting question here we're not going to answer, which is, so this says that rho is equal to 1 over phi, and we said that we're saying that phi is bigger than 1, so this is a number between 0 and 1, which is what we want. Who decides who's going to derive? I guess whoever starts first earliest in the morning or something, or if you flip coins, you have lottery tickets. We're going to leave that unsaid, but this is in equilibrium, we're going to have a condition like this being satisfied. All right, so this is what happens in the private case, where every individual is making an individual decision about whether to drive or take apart, and they're ignoring the fact that when they make that decision, they're going to wind up having an effect on congestion that affects others. Okay, is that clear? Okay, so yes. Oh, I'm assuming it's bigger than 1. If phi is smaller than 1, then this quantity will always be less than W. So it's just not an interesting case. It's always cheaper to take the bus regardless of how many people are driving in that case. So the interesting case is just the one where phi is bigger than 1. Okay, other questions? All right, yes. Phi is a parameter that governs how much having more people drive affects your commute time. So, and you might think it would depend on the route. So if you're thinking about a commute over the Bay Bridge, phi might be quite a large number. If you're thinking about a commute or someplace where there's not some sort of a bottleneck like that, phi might be relatively small. You might be able to have a lot of people driving without congestion being a big issue. So it maps how many people, what proportion of people are driving into the time, increase in time required for you to complete your commute. That's what phi is. You can imagine. I mean, if you have a particular route in mind, you can measure this pretty easily. If you got out your stopwatch, drove from Berkeley to San Francisco at midnight when there were no other cars somehow, then you'd be able to figure out the cost when rho was very small, and that would give a time cost, and you could do it, at some rush hour, and see how that affects your commute. You can measure phi that way, perhaps. Okay. All right. So this is the private solution. Now, note that there's a pattern here to the way we tackle these problems involving externalities. And so I've done several of these problems now. We always start by figuring out what the outcome is if everyone ignores the externality, if it remains external. What's the next thing we do? So we characterize the private outcome where the externality is not accounted for, not internalized. Very good. So we figure out the socially efficient thing to do. Okay, so let's work that out. So we've got a private solution here. Let's go ahead and characterize the efficient public solution. And the way I'm going to do that is by trying to write down an expression for the proportion of the population rho that minimizes the total commute costs for the entire population. So I'm going to internalize the congestion here by trying to make a decision for everyone all at once, the entire population. So if you imagine some social planner, some dictator who could decide, okay, we're going to allow some proportion rho of people to drive, that dictator would choose rho. They choose it to minimize the total social cost, and the total social cost in this case is going to look like this. There will be rho people who wind up driving, so their cost will be phi times rho squared times W. So this is the opportunity, so the opportunity cost of the time lost for all car drivers. So it's the cost of the commute for all car drivers. There's a proportion rho of the entire population. Yes. So we're doing it for the entire population, and a proportion rho of that population drives. So this is the cost per person, and we're thinking about everyone in society now, and a proportion rho of those guys are going to be driving. So that's where that outside rho comes from. Okay, so we got the drivers. Now let's do the guys on the bus. So there's 1 minus rho of those guys, and the social cost, the cost for them of commuting is just W. Doesn't depend on congestion. All right. So is that clear? Okay. So this is the bus time cost. But again, over all the people who are actually taking the bus, it's not just per person, it's for everyone driving the bus, yes. Rho is I call it proportion. Yeah, it's a proportion. It's a number between 0 and 1. It's the proportion of the workforce that's driving. Okay. All right, so now let's choose rho. So first order conditions here, well, we've got a rho that shows up here twice. So I'm going to rewrite this thing first. I'm going to minimize what rho, the thing that's going to show up here is going to be phi times W times rho cubed, and that'll be plus 1 minus rho W. And the first order condition for this is what? So, good. Yeah, we got a 3 from here, so 3 phi W rho squared, and then we have a minus rho here, so this is just equal to W. So this, and then some nice stuff happens here. The W cancels out. I can solve for rho, so let's call this rho star. This rho star is going to be equal to just the square root of 1 divided by 3 phi. So this is the optimal rho. Okay, compare that to the private rho we had. So that was this rho sub p was 1 over phi. This is 1 over 3 phi. All right, so that's good. So this tells us the social proportion.